Okay, so let's quickly have a look at last year's final paper, November 2022, and we're going to have a look at question 1. It's usually short answer questions. In this case, as you can see, it's multiple choice. Now, if you look at question 1, what they ask from you is to choose the correct answer. Now, let's jump to the first question. Question 1.1.1. Lines that join places of equal atmospheric pressure on a synoptic weather map are known as. Now, grade 12s, that's the beauty of it. So we've seen it before. This is the foundation when you started doing geography in grade 10. So this is almost like revision, isn't it? Because you know this answer. We've done it since grade 10 and in grade 11, and now it's repeated in grade 12 again. Now, lines joining places on a synoptic weather map is known as isobars. So if we quickly look at the options over there, 1.1.1, we've got isolines, isotherms, isoyets, and the correct answer will be D. 1.1.2. The wind direction represented by the station model below is. Now the options given to us: A, northwest, B, southwest, C, southeast, D, northeast. Now, before I'm going to answer this question, because if we'll look at our next questions, is regarding weather station models. Once again, grade 12, this needs to be a very simple topic for you because we've done it in grade 11 and in grade 10. Now, for instance, remember the 19 that we see in the top left-hand side corner represents temperature. The bottom number represents dew point temperature. The body of our weather station model represents the cloud cover. Right. Now, as you can see, the arm situated over there represents the wind direction. And the arm attached to it, the wind speed. Now we've learned about this, and in between temperature and dew point temperature, there's a space for a symbol to represent precipitation. But I reckon some of the next questions will go into that. So we've done this since grade 10. Now, very importantly, grade 12s. Our weather station model is represented as following. North will always be on top, east, south, and west. Now, this extension over here, like I've mentioned, represents the wind direction. Now there's north, east, south, and west. So what will be the correct answer? It will be southwest. So the wind direction will be southwest. So our correct answer over there will be B. If we look at our next question, and this is what I just mentioned a couple of seconds ago, our precipitation. Okay, if you look at question 1.1.3, which one of the station models below shows drizzle as a form of precipitation? Now, as you can see, first and foremost, precipitation that we see over here is this symbol over there. This symbol represents thunderstorms, but most importantly, it's been written on the wrong side. It's always been written on the left-hand side. This is known as fog, and this is known as hail. So our correct answer for 1.1.3 will be A. That will be our correct answer. Now, very interesting one over here. A diagram has been provided. Now, grade 12s, you will see when I discuss the question papers with you, before even looking at the questions, let's see what's been given to us. And let's try to understand what's given to us and what do we see that's been provided. Now, we need to answer question 1.1.4 to 1.1.6. Now, first and foremost, let's just quickly identify what I see over here. We see a low pressure system over the interior. represented with an L. Right, situated on the bottom left-hand side corner, that's the South Atlantic high pressure. We can see the isobar reading is above 1013 hectopascal. Bottom eastern side, we have the South Indian high pressure system. Okay, now very importantly, one thing I can tell you immediately, if you look at this diagram, what season will it represent? I'm going to say summer, and the reason why I know it is because we have a low pressure over the interior. Now once again, we need to revise what we've learned in grade 10 and 11, when we distinguish between a low pressure and a high pressure, right? A low pressure is rising air. A high pressure is sinking air. Okay, so this low pressure over the interior exists because of warm conditions. Now very importantly, grade 12, once again, we've learned about this. South Africa is situated on a 30-degree latitude line, also known as what? The subtropical high pressure belt. So we are dominated by high pressure systems. Yes, it's probably going to be one of our questions a little bit later on. We do have a high pressure over the interior of South Africa, but only during winter. That's the Kalahari high pressure system. It's present, but it's very high in altitude and it's extremely weak. Okay, so we have identified the South Atlantic high pressure. We have identified a low pressure over the interior. We have identified the South Indian high pressure. We can see the temperatures are mild. We have 20 degrees, dew point temperature 18, full cloud cover, wind direction is northwest, and a wind speed of 10 knots. Now let's just quickly look at the questions and see if we might have answered some of these questions while we looked at this diagram. Okay, now if you look at question 1.1.4, the atmospheric pressure reading at A, and let's just quickly look at A, right? They want to know what's the pressure reading being experienced at A. Is it 1004 hectopascal or millibar, 1008, 1012, or 1016? Now remember, the interval for isobars is 4 hectopascal. Right, so that's 1016, that's going to be 1012, so that means A is going to be 1008. So our correct answer for 1.1.4 will be B. As you can see, please pay attention to the isobar interval, 1020, 1060, 1012. From here we go, there's 1016 going all around, there's 1016, as you can see is decreasing, 1012, and the next isobar is going to be 1008. Now, if we quickly have a look at question 1.1.5, the feature B is known. Now that's an interesting question because we are having two high pressure systems opposite each other. There's high pressure system 1 and 2, and they're discussing B. It's this area between the two of them, and the correct answer will be a saddle. A saddle is an area between two high pressure systems, as you can see. And the correct answer for 1.1.5 will be D. If you look at question 1.1.6, the low pressure cell over the interior has caused northwesterly winds because of what type of circulation and overcast conditions due to descending or ascending of air. Now, very interesting question. And I actually forgot to mention this when we look at this diagram. Another characteristic of a low pressure system is that in the southern hemisphere, we have clockwise circulation of air. High pressure systems have anti-clockwise circulation of air. So if we can look at this low pressure system over here, we have clockwise circulation of air. So that answers our first question. If we go back to our question, the low pressure cell over the interior is called northwesterly winds because of clockwise circulation. And the overcast conditions is due, because we've already mentioned this, descending or ascending air. Now, what's the difference between the two? One is going up, one is going down. Right, now if we quickly have a look at it, like I've mentioned over there, as you can see, low pressure systems, we have rising air and sinking air. So the correct answer for 1.1.6 will be C. The correct answer is clockwise and ascending air, as you can see. That's the correct answer for 1.1.6. Now let's have a look at question 1.7. Once again, we have a diagram. Now, before we have a look at the questions being asked, let's decipher this diagram and see what's being asked over here. Okay, first of all, let's look at our weather station models. Interesting one, very interesting one, and I'm going to call it. This diagram is based on winter. How do I know that? First of all, have a look at our temperatures. 16 and 14. That's quite cold, am I correct? Especially over the interior, right? Now, look at the dew point temperatures. -10, -8. Very interesting as well. If you look at our weather station models, clear skies. 0 octus. So that's clear skies. Now you should know now, grade 12s, over the interior, during winter, we experience clear blue skies. Why? Because we have the Calaria high pressure system over the interior. We have sinking air. So there's no formation of clouds possible because of the strong subsidence taking place. As the weather station models indicate, as you can see, all three of them over the interior is clear blue skies. Interesting one over here. Just want to point this out. It shows us again, there's a coastal low pressure that we experience over here. Now, coastal low pressure, as the name indicates, it's a low pressure that we find at coastal areas. As you can see, remember the anti-clockwise circulation. No, apologies, clockwise of circulation of air. Once again, we have the South Atlantic situated over here. High pressure. Remember, anti-clockwise circulation of air taking place. Now let's have a look at our question. 1.1.7, the low pressure cell in the sketch, I've mentioned a couple of seconds ago, is a coastal low pressure. Okay, and the correct answer will be C. 1.1.8, the interior of South Africa experience what type of conditions with a greater temperature variation due to what type of climatic conditions? Okay, very importantly, once again, prior knowledge has been tested over there. You've learned this in grade 10 about maritime climate and continental climate. Maritime climate, think of marine. Where do we find marine? Close to coastal areas. We have, if you look at the temperature variation at coastal areas, are much smaller than those in the interior because of terrestrial radiation, right? Water, the ocean has an impact. It has a cooling effect as well as a warming effect. Cooling effect during the day and a warming effect during nighttime because it releases heat much slower. Continental climate, right? big variations. What happens over there? The land warms up, terrestrial radiation takes place, it cools down. Okay, in this case, the interior of South Africa experiences what type of conditions? Stable conditions. Stable conditions because we have the Kalahari over the interior, we have sinking air. Unstable conditions when usually we have cloud formation taking place, we have rising air, convection taking place, there's a build-up, we might experience thunderstorms. In this case, definitely not, because we looked at our weather station models, all perfectly clear blue skies. And definitely it's continental. So our correct answer is going to be 2 and 3. And what will be our correct answer for 1.1.8 is going to be the letter D. Okay, question 1.2. Right, once again, short answer question. Very importantly over here, know your concepts. Vitally important, especially with geomorphology, when we look at drainage basins. Okay, let's match column A with column B. Now let's just quickly have a look at this. Complete the statements in column A with the options in column B. Write down only letter Y or Z next to the question. Now, if we quickly have a look at question 1.2.1, increased absorption of heat in urban areas is due to artificial surfaces. Okay, let me just quickly elaborate about this. When we look at urban areas, and let's go back, urban heat islands. Urban areas, what's an urban heat island? It's an urban area warmer than the surrounding rural areas. The simple reason why is because there's so many more artificial surfaces, such as tar roads, concrete buildings. So what do? They absorb more heat. And that's what's being discussed in question 1.2.1. Increase in absorption of heat in urban areas because of artificial. It's fake. Now, if you look at natural, if you look at rural areas, it's covered with vegetation, it's covered with trees. Now, that has a cooling effect on the rural areas. Now, if you look at question 1.2.1, the intensity of multiple reflections of heat is increased due to the dimensions of buildings. And the correct answer over there is Y. Now, because of the reflection taking place, reflection doesn't just take place horizontally. It goes back vertically. Okay, now we're talking about glass. We're talking about mirror type of buildings, reflecting the insulation that comes in. If we look at question 1.2.3, the air pressure will generally be higher or lower in urban areas than in rural areas. And the correct answer will be lower. Now, the simple reason why, we just mentioned it. What happens with low pressure? The air rises. High pressure, the air sinks. So you can just imagine, when we look at urban heat islands, warmer conditions, air rises. Okay. Colder conditions, air sinks. So the air pressure will generally be higher in urban areas than in rural areas. We just discussed rural areas are going to be much cooler because of vegetation cover. Okay, there's less artificial surfaces. Very important. If we look at question 1.2.4, the wind speed in urban areas is faster or slower than in rural areas. It's definitely slower. So the correct answer for 1.2.4 is going to be Z. Why is it going to be slower? We have obstacles. There's going to be more friction because of high-rise buildings. Wind is going to be channeled, right? If you look at Johannesburg CBD, comparison, if the wind needs to blow in Johannesburg CBD, comparison to a rural area that's covered with veld, right? So these buildings create obstructions. So it's definitely going to be slower, the wind speeds. If we look at question 1.2.5, the relative humidity over urban areas is lower than that over rural areas due to more or less evaporation. So the correct answer there will be less evaporation. The simple reason why, if you compare an urban area with a rural area, Rural areas might be covered with open water surfaces. There's more plants, there's more vegetation. If you look at urban areas, it's a concrete jungle, right? There's less moisture in the air because it's artificial, right? The air is dry. Think of the amount of pollution that's being created as well. So definitely less evaporation is going to take place in our urban areas than our rural areas. If you look at our next question, 1.2.6, urban areas have a higher frequency of precipitation than rural areas due to hygroscopic particles or building structures. Now the correct answer over there is hygroscopic particles. Even though urban areas have a drier type of air, right? The air rises. So what happens, because it's artificial heating taking place? So this warm air attaches itself to hygroscopic nuclei, and eventually when it rises, it condenses clouds and the formation for rain, possibility of rain to take place. That's the reason why it rains more in urban areas than surrounding rural areas, because of the heat, artificial heat that's being generated, and it attaches itself to the hygroscopic particles. Now, if we look at our last question in our column, 1.2.7, the temperature graph, Y or Z, represents the changes in temperature from the urban area to the rural area. Now, if you look at that, 1.7, the correct answer will be Z. Now, from the urban area. So S represents the urban area, and T represents the rural area. Now, clearly, as you can see, our x-axis represents temperature. As we move closer to the urban areas, what happens with our temperature? There's an increase of temperature because of artificial heating taking place. Okay, that sums up our short answer questions. Let's move to our next question. And this is where our paragraph questions comes in. Now, when we look at question 1.3, once again, grade 12s, before we look at the questions, let me do explaining what I see in front of me. Now, when you do have your reading time, go and look at these diagrams. Okay, now, first and foremost, we've been given here 3 diagrams. And we have a plan view, that's from above, and we have a cross section from the side. Now, grade 12s, what I see over here is a mid-latitude cyclone. They've even given us the topic on the bottom of the diagram. Pay attention to the following, please. Mid-latitude cyclones move from west to east. Now, the reason why it moves from west to east, because it moves in the westerly wind belt. Okay. Unfortunately, I can't use my blue pen because we're on a blue screen over here. Just want to get the right, I'm going to use yellow. So as we can see over here, we have our cold front. And over here we have our warm front. And one thing immediately, the cold front is caught up with the warm front. And what I see in these 2 diagrams from the plan view, that the cold front has already caught up with the warm front, as you can see over here. And that is known as the occluded stage. Okay, very importantly, the cold front is the leading edge of cold air. Everything behind it is cold. The warm front is the leading edge of warm air, as you can see. Now remember, what's the air like in front of the warm front? It's also cold. This is the cold sector right over here. Stretches from in front of the warm front to the cold front. Remember, the cold front is the leading edge of cold air. The warm front is the leading edge of warm air. Now once again, just let's cover the basics. What is a front? A front separates two different masses of air. In this case, the cold front separates warm air from cold air. Same as the warm front. Okay, let's just quickly move to our cross sections. So once again, I'm going to use my yellow pen to show the cold front. There's the cold front. Okay, and diagram Z, there's the cold front. Very importantly over here. Our warm front, as you can see, it's the occluded stage because the cold front has caught up with the warm front. As you can see, there's the warm front. Now, without looking at the questions, let's just quickly have a look at this. Pay attention to the temperature of the air. Cool air, cold air. Cold air, cool air. Now grade 12s, what we have here, we have two different types of occlusions. We have a warm front occlusion and we have a cold front occlusion. And it's so easy to identify which one is which. And I'm going to show you on these diagrams quickly. Now, if we look at Y is a warm front occlusion. Now, how do I know that? Very importantly, pay attention. The air in front of the warm front is colder than the air behind the cold front. So what happens over here? The warm front attaches itself to the surface, right? Because when we look at air, where will we find the coldest air? Closest to the surface, because it's more dense, it's heavier, right? It sinks much faster. So the coldest air will be closest to the surface. Now, just use this example just this as an example. When you jump into a swimming pool, where's the water the coldest? At the bottom of the swimming pool, right? So in this case, once again, going back to my diagram, the air in front of the warm front is colder than the air behind the cold front. So the warm front attaches itself to the surface. Now, opposite story happening at Z, right? Pay attention to the air behind the cold front. The air behind the cold front is colder than the air in front of the warm front. So this is known as a cold front occlusion. And what happens over here? The cold front attaches itself to the surface. Right? Once again, coldest air closest to the surface. Why is the cold front occlusion? The cold front attaches itself to the surface. Upliftment is taking place, this occlusion stage. The air behind the cold front is colder than the air in front of the warm front. Now, let's just quickly have a look at the questions as being asked. Oops, sorry, I just need to scroll down. Okay, if you look at our first question, question 1.3.1, name the wind belt that causes the easterly movement of the mid-latitude cyclone. Believe it or not, here's our answer right above us, the westerly wind belt, because it moves from west to east. Remember, wind is named from the direction it's coming from. Vitally important. So our correct answer is right there, westerly's wind belt. Now, if you refer to the plan view, question 1.3.2, identify front A. Now, like I've mentioned, we studied our diagrams. What is the front at A? It's the cold front. So we have already answered it because we identified it when we looked at our diagrams and interpret our diagrams, very importantly. And that's the beauty of climate, grade 12s. All the answers is usually in your diagrams. Okay, just need to be able to identify them. So the front is the cold front. Okay, 1.3.3. Which one of the fronts, A or B, is moving faster? Now, our summer learners, it's like cowboys and robbers, right? What basically happens over here? The cold front is the cowboys and the robbers is the warm front. But it's inevitable that the cold front, the cowboys, is going to catch up with the robbers. So that's what's happening over here. The cold front always catches the warm front. So the cold front is going to catch up with the warm front. Inevitably, it's going to happen, right? If I can show you. So definitely A, let's just go back. We identified A as the cold front and B as the warm front. So the correct answer is definitely going to be A. Now, when we look at the movement of a mid-latitude cyclone, as you can see, right, it moves in stages. And this cold front closes the gap between the warm front. And eventually, it will become occluded when they have caught up with one another. Okay. So we can almost say that the warm front is quite stationary. It's inevitable that the cold front is going to catch up with the warm front. Okay. If we just have a look at it, 1.3.4. Right, give a reason for your answer to question 1.3.3. Now, first and foremost, we need to go and look at our diagram. They asked us to go and have a look at our diagram, right? And have a look at our weather station models. Look at the wind speed behind the cold front, and look at the wind speed in front of our warm front. Apologies, behind our warm front. Only 10 knots being represented where the warm front is, but 30 knots behind the cold front. Now, almost basically 3 times faster than the air behind the warm sector. Okay. So we can just write down there the wind speed behind the cold front is 3 times faster. Or you can mention that the wind speed behind the warm front is 3 times slower. Okay. Now 1.3.5. Give evidence from the sketch that the mid-latitude cyclone is found in the southern hemisphere. Now I can give you a tip over there. A cyclone, we know, is a low pressure system, and we know that it's clockwise circulation of air. Now let's just quickly have a look at the diagram. Here you can see it's been pointed out that there's a clockwise circulation of air taking place over there. So we're going to stick to our answer, even though we know that cyclone is a low pressure system, it's clockwise circulation. Okay, our next question focuses on our 2 cross sections that represents Y and Z that we discussed. 1.3.6. Which one of the cross sections, Y or Z, represents the cold front occlusion at sea? Now let's go back to our diagram. So this is our occlusion. It's when the cold front is caught up with the warm front. So the question states 1.3.6. And the correct answer is the cold front occlusion is Z, situated over there. How do we know it's a cold front occlusion? The air behind the cold front is colder than the air in front of the warm front, and the cold front attaches itself to the surface. Okay. So the correct answer over there is Z. Okay. Give evidence that C is a cold front occlusion. I'm just going to draw it for you over here, right? There's the cold front. The cold front has attached itself to the surface, has uplifted the warm front, because the air behind the cold front is very cold. The air is cool over here. All the warm air has been displaced, right? Or we can say over here, the air behind the cold front is colder than the air in front of warm front. Now, if you quickly have a look at this, C, explain how the cold front occlusion developed. So first, if you look at the mark allocation, 2 times 2 is 4. Now, first and foremost, what we can mention, the cold front moves faster than the warm front. And undercuts the warm front. And when that cold front undercuts the warm front, it forces the warm front to rise, warm air to rise. Resulting in the narrowing of the warm sector. Okay, now once again, just want to go back to my diagram. Immediately we can identify this as a occluded stage, because you can see the warm front is cold front is caught up with the warm front. You can see the cold front is moving much faster. Look at the wind speed behind the cold front in comparison to that of the warm front, right? Over there, if you look at our cross sections, what do we have over here? We have a warm front occlusion, because the warm front attaches itself to the surface. The simple reason why is because the air in front of the warm front is colder than the air behind the cold front. Different scenario over here. We have a cold front occlusion. We can identify it over there because the cold front attaches itself to the surface. The air behind the cold front is colder than the air in front of the warm front. Let's quickly look at our next question. Question 1.4. Refer to the infographic below on a tropical cyclone, Batsirai. Okay, immediately, grade 12s, what's been given to us is a satellite image, and we see a path of this tropical cyclone. Now let's just quickly go back. Once again, I've mentioned with the previous question, a cyclone is a low pressure system. Tropical cyclone, that's what we call them in the Indian Ocean, and what we call them here in South Africa, right? America, it's known as hurricanes. In Asia, it's known as typhoons. Okay, so different names over the world. But most importantly, when we look at tropical cyclones, think of the name, the tropical. It forms in tropical regions. Now, when tropical, we immediately think what? Warm, humid. Okay, so we're looking at warm conditions, tropical conditions where these cyclones develop. And if you can think of it, if you just look at the world map, where do we find tropical regions? Close to the equator, am I correct? Because they only experience one season, always warm and humid along the equator. Now, if you quickly have a look at our graphics, infographics as being supplied to us, right? First and foremost, I can identify Johannesburg over here. That's the continent of Africa. There's Mozambique. There's Madagascar. Right? So we know immediately it's in the southern hemisphere. Immediately we know that. Not only because of the name, right, tropical cyclone, but we can see Africa, the continent over there as well. Now roughly, if I can look at this diagram, if you look at the path of the tropical cyclone, this is roughly where we're going to find the equator. Now, very important tip, remember, tropical cyclones can't form between 0 and 5 degrees north and south of the equator in this area because there's not enough Coriolis force. And the wind belt that we experience from 0 degrees to 30 degrees, there's the 30-degree latitude line. I'm just going to use a different color pen quickly. It moves in the tropical easterlies. As you can see, it moves from east, there's the path, to west. And now remember, when it gets to the 30-degree latitude line, what does it do? Right? It's probably going to move like that, and then it's going to recurve, and it dissipates, it dies out. Because the ocean water is too cold over here. Now, once again, you can see the symbol of a tropical cyclone on a synoptic chart. Usually it looks like that. Perfectly shaped round isobars, very close to one another. Now, isobars are lines joining places with equal pressure, a pressure well below 1,000 hectopascal. They are very close to one another, and we look at the pressure gradient, what we've learned in grade 11. When these isobars are very close to one another, it's very strong winds, steep pressure gradient. Now, as you can see, there's the satellite image, right? We can see the beautiful clockwise circulation of air. We can see the eye of the storm perfectly clear over there. Okay, and you can see the buildup of cumulonimbus clouds, cumulus nimbus, okay. Now, as you can see, the wind speed, right, how intense it's over there at the 20th February, right, and it decreases over time. As you can see, the tropical cyclone Bhattarai intensified and moved west across the South Indian Ocean. There you can see it moves from east to west, right? The forward movement was approximately 19 kilometers per hour. Bhattarai made landfall on Saturday night with winds and rains, caused considerable damage, right? And transport links. Now keep in mind, when we look at tropical cyclones, always think of the economic, social, and environmental impact. Grade 12s, I can't emphasize enough how dangerous the storm is, how dangerous a tropical cyclone is. We experience storm surge, we experience wind speeds up to 250 kilometers per hour, right? It's extremely destructing, right? Especially for countries in Southern Africa, that's mostly developing countries. Okay, now let's quickly have a look at the questions that's being asked regarding tropical cyclones. 1.4.1, if we look at the question, give the date on which tropical cyclones Bhattarai reached the mature stage. Now they've mentioned it in the case study, right? It's on the 20th of February. So that's the correct answer. And how do we know it's a mature stage? Pay attention to the wind speeds, highest. Okay, so that's when the tropical cyclone is at its most dangerous because excess amount of wind speed has been reached. Okay. According to the infographic, tropical cyclone Bhattarai moved westwards across the South Indian Ocean. Give one reason for the movement. Now, I've shown you on that diagram because it moves in the tropical easterlies. So that's our correct answer. tropical easterlies. Sorry, I just should have mentioned moves. Okay. Now, if you look at our next question, suggest 2 reasons for the large decrease in wind speed between the 20th and the 25th of February. Now, when we look at our graph, you can see from the 20th till the 25th, there was a massive decrease of wind speed. Now, the simple reason why, because as this tropical cyclone moves from east to west, it has moved over Madagascar. Now, you need to remember the fuel for this tropical cyclone is warm ocean temperatures above 27 degrees Celsius. That's the reason we experience them mainly late summer, early autumn. That's when our ocean temperatures are warmest, after the summer season. Right? Vitally important. It needs a lot of humidity, latent heat, and convection for this tropical cyclone to build up. Now, eventually what happens, as soon as it makes landfall, it loses its fuel, like a car running out of petrol, because it's moving over land. There's no source of energy, latent heat, evaporation, nothing like that. Like I've mentioned, it needs ocean temperatures above 27 degrees Celsius. It moves over land, not only for its source of energy, friction is being created because of the uneven topography that's being experienced on land. Okay, so that answers our question over there, but let's go back to our question. And that's the reason why there's a decrease in the wind speed. Okay, so immediately we can say the tropical cyclone has reached land. We can also mentioning there's friction over land. There's going to be a decrease in moisture. And there's going to be less latent heat, because it's situated over the land. Now, if we look at question 1.4.4, how could storm surges negatively impact the physical environment on the east coast of Madagascar? Now, I've mentioned storm surges briefly a couple of minutes ago. Storm surge is when the wavelength increases at coastal areas. So the waves becomes bigger and bigger and bigger. The simple reason why is because of the wind speed. So as the wind increases, the waves increases in size. Now you can just imagine the impact that it will have on the coastal regions, not only in infrastructure, but even on the environment, causing more soil erosion, etc. But let's quickly have a look at the question and answer it directly. How could storm surge negatively impact the physical environment? So they're asking about the physical environment. First and foremost, the coastal areas can be flooded. There will be an increase in soil erosion. We might experience mass movement. And lastly, pollution of water resources. And destruction of habitats. Now if you look at our next question, 1.4.5, explain the importance of monitoring tropical cyclones like Batsirai from Madagascar. Now this is vitally important, grade 12, especially if we look at Madagascar as the developing countries. We need to alert people as soon as we track images of tropical cyclones approaching, because like I've mentioned to you before, it's a deadly storm. I think there's nothing that can prepare you. I don't think you can ever be ready for a storm of this magnitude, because like I've mentioned, we have torrential rains. Just to give you an example, Johannesburg experienced an annual rainfall of between 600 and 800 millimeters of rain a year. That amount of rainfall can fall over 3 consecutive days when a tropical cyclone do take place. So we have huge amount of rainfall taking place. So it's definitely going to be flooded, the areas. We have wind speeds, massive wind speeds, destructive wind speeds. And if you look at it, as well as developing countries, most of the infrastructure, housing, is built like informal settlements. It's not the strongest infrastructure that we have. But we need to prepare for such an event. And how can we be prepared for such an event? First of all, we need to rely on government assistance, and we can mention over here early warnings, systems in place. Another thing is we can observe the path or study the path of the cyclone. Another thing is, with today's technology, we can do advanced weather forecasting. And very importantly, evacuation plans and emergency services on standby. Now, if we quickly move to our next question. If you look at question 1.5, refer to the sketches below showing the changes in the position of the inversion layer of South Africa. Very interesting over here. What we're dealing over here, grade 12s. Let's have a look at our diagrams. Now, we experience the inversion over here. First and foremost, with South Africa, if you look at South Africa's topography, we have a plateau. It's a high-lying area. This over here is known as the escarpment. As you can see, I'm just going to mention over here, Johannesburg. Now, as you can see, we have the warm ocean current over here, so we can assume this is the east coast of southern Africa. Over here, we have a cold ocean current, and we can assume this is the west coast. Now, once again, we just revise our previous knowledge. This cold ocean current is known as the Benguela current. The warm ocean current is known as the Mozambican current. Very importantly over here, weak descending air. Now, we know the warm Mozambican current creates, as you can see, warm, moist air. We know that the cold ocean current, the Benguela current, creates cool, dry air. Now, they've mentioned in diagram A, it's a weak descending air. So immediately, grade 12s, I can identify this as conditions during summer. Why do we have weak descending air in summer? Because the Kalahari is much higher in altitude. We experience warm temperatures because it's summer. So the Kalahari, as you can see, is extremely weak. So the inversion is above the escarpment. And as you can mention, I just want to wipe this out because there's some important information. As you can see, they've mentioned over here wet conditions that's being experienced. Why? The reason why is because this warm, moist air is able to go over the escarpment onto the plateau. It's allowed to rise, cool, condense clouds, and rain. Now, at B, we have the Kalahari present during winter. So, this is definitely summer. In diagram B, we have winter conditions. Why? Because we have a very strong subsidence taking place over here. And that is because of the Kalahari high pressure system over the interior of South Africa. Now, as you can see, because of the strong sinking air, strong subsidence, the inversion layer is below the escarpment, as you can see. So what happens over here? This warm, moist air coming from the Mozambican current and cool, dry air coming from the Benguela current is trapped below the inversion layer. None of this air can go over the escarpment to the plateau. It's not happening. So what do we experience over the interior of Southern Africa? Dry conditions and clear blue skies. Okay, now let's just quickly have a look at the questions that's being asked regarding these two diagrams. But first and foremost, A definitely represents summer and B represents winter because we have the Kalahari, strong subsidence, descending air that we experience over the interior on the plateau. Now let's have a look at the questions. Identify the season illustrated in sketch A. Like I've mentioned, with all the information given to us, the correct answer will be summer. Now if we look at our next question, give a reason for your answer to question 1.5.1. The simple reason why is we saw it, it's weak descending air. And we can see the inversion is above the escarpment. If we look at sketch B, identify two factors visible in the sketch which influence the climate of South Africa. Now, the first one, and you've learned this in grade 10. Now, let's quickly go over these factors quickly. Factors influence the climate of South Africa. The first one is altitude. Okay, altitude, height above sea level, and that's the plateau. Now, in Johannesburg, if you look at this diagram, we are situated on the plateau. Now, down here next to the warm Mozambique current is Durban. We are roughly in Johannesburg 1,600 meters above sea level, much higher than the coastal areas. Okay, so altitude definitely, we can also refer to the plateau. Another factor, distance from the sea. That's the reason we have maritime climate and continental climate. Okay, another factor, latitudinal position as well. Okay, but when we quickly answer this question over here, first and foremost, the plateau, like I've mentioned. Then again, ocean currents, forgot to mention that because we looked at our diagram. We have the warm Mozambican current, we have the cold Benguela current, creating cool, dry conditions, the Benguela current, warm, moist conditions, the Mozambican current, latitude, and we can mention altitude. If we quickly have a look at question 1.4, explain the role played by descending air in the development of the inversion layer. Now, it's very simple. How stronger the descending air, how more compressed it makes the inversion layer. Right? So it creates the inversion layer to move downwards. So it forces this warm ocean air not to reach the escarpment. So as we can say, we can mention over here, the subsiding air compresses and heats up adiabatically. Okay, now once again I'm going to use Johannesburg as an example. Right, any place over the interior, we got strong descending air taking place over here. The air sinks, but what happens? It warms up adiabatically during the day. Okay, because of insulation. Now that creates the inversion. Now just going back to inversion, and this is very important terminology. It's an increase of temperature with a increase with altitude. Now, altitude is height above sea level. That's the correct concept for inversions. So, as you can see, the inversion that's being created, we go from warm to cold to warm. As you can see, that's a normal lapse rate. We're going from warm to cold, but then we go from cold to warm because of adiabatic heating taking place. Okay, if you look at the last question, 1.5.5, refer to sketch A and B. In a paragraph of 8 lines, describe how the position of the inversion layer in sketch A and B influenced the amount of rainfall in the interior of South Africa. Okay, I'm quickly going to use our diagram to explain it. And let me just quickly wipe everything out here. Now, how does it influence the rainfall in South Africa over the interior? Now, first and foremost, we discussed, right? The inversion, the Kalahari high pressure is weak. Right? As you can see, there's a very weak descending air subsidence taking place. So this allows for warm, moist air to reach the escarpment. Right? Very importantly, this cool, dry air coming in from the beginning of the current is just important because maybe we might experience line thunderstorms that develop because of when there's a moisture front, when there's cool, dry air coming from the one side, warm, moist air from the other side, we experience a moisture front. The cool, dry air forces the warm, moist air to rise, and we experience line thunderstorms. Okay, that can happen in summer. But inevitably, what happens over here? This warm ocean, this warm, moist air is allowed to reach the escarpment. So usually we experience a low pressure over the interior of South Africa. Now, low pressure, as we know, is rising air. Air rises, there's warm, moist air coming in, there's moisture coming in. The air rises, it cools, it condenses clouds, and we have rain over the interior of South Africa. Now, different story in winter. Unfortunately, there's a very strong subsidence, sinking air because the Kalahari high pressure is present and it's colder temperatures. Now, as you can see, the inversion layer is below the escarpment. So as you can see, all this warm, moist air is being trapped below the escarpment. It can't reach the interior. So that means we're going to experience dry conditions, no cloud formation because we don't experience any moisture in the interior. Now, if we just can summarize it quickly and we answer the question, Okay, how the position of the inversion layer in sketch A and B influenced the amount of rainfall in South Africa. So let's look at sketch A. What can be mentioned? First of all, the inversion is above the escarpment. Allowing moist air to reach the interior. We can also mention this, right? Lastly, we can also moist air to reach the interior, which might result in rainfall. Now, if we look at diagram B, okay, the inversion is below the escarpment. And we can mention moist air is trapped below the inversion. And that results in dry conditions. Dry conditions or no rain. And that, guys, is question 1, all wrapped up, done and dusted.